Then again, good afternoon, you all, and welcome to the CYU 4301 day school, not the compulsory day school. You have already discussed the session 1 and we have already discussed the session 1 and 2 during the compulsory day school. So today I hope to start from the session 3, and the session 3 is the relationship between the conductivity and the chemical composition.
Hello, madam. Hello,
Sorry?
madam.
Yeah.
Can you hear me?
Yes.
Madam, are we getting what kind of paper for the cat too?
Actually, I don't know. Maybe MCQ,
Okay.
no? Sorry, I don't know because it says MCQ or structure type. Then be ready for both. Then, if the coordinator said it is okay, then I am not a coordinator of this course. Only the teaching part is doing for the electrochemistry. So it is better to contact the senior coordinators. Okay. Then session 3, the relationship between the conductivity and the chemical composition of a solution. Then you have already know what is conductivity and what is the relationship between conductivity and the resistivity likewise. Then we'll move to the today's discussion, drift velocity. What does it mean? You all know that the frictional force due to the viscosity, when you consider a solution, you know there is a viscosity. In your physics, you have already learned that one. Then there can be a frictional force due to the viscosity. And in addition to that, frictional force is proportional to the velocity of ion and opposes its movement. You know, when you consider a solution, you have ions there. Then ions are moving for one direction. And also viscosity is there. Then what happens? The frictional force is opposite to the direction of the ions. And it is proportional, the frictional force proportional to the velocity of the ion. But the directions opposite. In a very short time, these two forces are balanced and velocity of each ion reaches a constant velocity that is called as drift velocity. For a very short time, what happens? These two forces balance. Then the velocity of each ion reach to its drift velocity. We call constant value it reach, that is called as drift velocity. Then what is drift velocity? Drift velocity is the velocity of each ion when it balances the forces of frictional force and the velocity of ion. A positive ion travels a distance v plus in a second. Here, the abbreviations are given according to the positive ions. This is distance travel v in a second. Velocity is, you know, ms minus 1. Then the distance velocity v is given for a second. Here you can see a box with the V plus and the V minus. If you consider the positive ions moves from S to X, and the number of moles inside this volume is equal to what? A is the cross-sectional area. V plus is the height. Then you can get the volume by A, V plus, and you can multiply it by the concentrations to get the number of moles. Got it? You know, number of moles is, concentration is number of moles per cubic centimeter or per volume. Moles per volume. Concentration is moles per volume. And you can get the volume of the cube by getting the cross-sectional area A's and the distance traveled by the positive ions is V plus, then you can get the volume by AV plus. And when you multiply it by the concentration, you can get the number of moles of positive ions inside this cube. Similarly, you can find out the number of moles inside this cube as well. It is AV minus multiplied by the concentration of negative ions. Sorry. Then when you study the session 1 and 2, you got the relationships. Q is equal to NFV, Z. We are not giving this equation in your paper. You should memorize this one. Q is equal to F Z. Those are basic equations. And you should know what is N, what is F and Z. And also you know Q is equal to I over T. Or I is equal to Q is equal to charge is Q is equal to I over T. And whatever it is easy to memorize, keep it in mind. Usually I am getting I is equal to QT. What is the given easy thing? It is better to memorize. Then you should know this equation also.
Madam, Q equal IT, no?
Yeah. Q is equal to IT. I also confused, that's why. Okay, Q is equal to IT. But here something wrong, I can't. Here Q, you have to change it as, sorry, IT. Sorry, yeah. Then you can get Q is equal to IT. Then what happens? Q is equal to IT and Q is equal to NFZ. These two equations you should memorize. And also I is equal to what? What is given? Number of moles, what we calculated here. This is number of moles, Z and F. Here also, instead of T, it is given to here. Because we got this per second. Therefore, this T comes to here, then I is equal to N over T F is it. Then what is N over T is here. Similarly, for the negative ions, you can get it is as A V minus C minus for N over T. Number of moles per travel within a second. Then Z is the charge number, F is the Faraday constant. Then the total current created inside this here is equal to the current created by the positive ions and the current created by the negative ion. Q plus, sorry, I plus plus I minus. Then you can add them together to get the value. Then it is equal to this one. You can get the A out and you can simplify it like this. Then I'll clear the drawing. Then what is here? Here you can get the A out and V plus C plus Z plus F, and you have V minus C minus Z plus is F. Then you can find out the J. What is J? What is J? What
Current
do you?
density.
Current density. Current density is equal to I over A, current over area. Then you can separately find out I plus over A, I minus over A. Then you can divide the whole thing by A. Then what happens? A, you can cancel this A to this A. Then you will end up with this equation. This is the current density due to positive and negative ions. And also we proved that J is equal to K, so Ke. What is K? Kappa E. Then what happens? J is equal to kappa E. Then here you can write down what is J. It is what we derived earlier. Then conductivity is equal to what? Kappa. You have this relationship now. Then you can separately get the relationship between the positive ions. What is the value? Kappa plus C is equal to V plus C plus Z plus F. Then you can divide it by E and you will end up with this equation. For the positive ion, kappa plus equal to drift velocity V plus over E, C plus Z plus F. For the negative ion, similarly, you can write down it for this. Then ionic mobility is equal to drift velocity over electric field. Here, drift velocity, what is drift velocity? It is V plus over E for the positive ions, V minus over E for the negative ions. Then mobility is equal to V over E. Then again you can rewrite this equation by adding the ionic mobility is U. U is equal to V over E. Then you can write down the kappa is equal to kappa plus and kappa minus, and it is equal to mobility of positive ions concentration and the Z plus mobility of negative ions concentration and Z, and finally you have to multiply it by the Faraday constant. Then this is the way how to derive. In your exams you can see some equations are given. What is the relationship between this kind of relationships given? Then see what are the relationships given in your final exam papers. Then you do not need to memorize them all, but these two equations you should memorize, and also this one, and the relationship between the positive and negative ions. Total current is equal to each and can get by using the current created by each and every ion. These are the relationships you should memorize. J is equal to kappa E is given most probably. Note, if you can measure the ionic mobilities, then you can calculate the conductivity. See, can you calculate the conductivity if you can measure the mobility? For a given solution, we know the concentration and the positive ion Z and Faraday constant. Charge number we know. Then if we can measure the mobility, then we can get the conductivity of the solution. Similarly, negative ions also. Then there should be a method to find out the ionic mobility of the ions. This is the experimental determination of ionic mobility, and we call it as moving boundary method. With the name, you can see what is it. Moving boundary. What is moving? Boundary is moving. From where to where we are measuring. The boundary. Here you can see the distance x. And boundary at the beginning we call it as P. And we assume that it end up at the Q, and we can get the distance from P to Q and mark it as x. This is the distance traveled by the boundary. Then we'll see how to get the setup. Can you tell me what is the positive terminal and B, A or B? Positive terminal? Connect to A.
A.
This is positive. This is negative. Then what is the difference between two solutions given? Cadmium chloride and the potassium chloride. What is the difference?
Is it color?
Sorry? Color.
Cadmium
No.
chloride has the color.
Sure. Maybe if it is a D element, please see it. Okay. Then when you consider these two, you can see same anion. Is it correct? Same anion, only change the cation. Observe the rate of movement of a sharp boundary between two solutions having an anion or cation common. Therefore, when you are measuring the x for a given solution or about the distance traveled by the boundary, you have to keep anion or cation in both solution in common. Here what is common? Both chlorides are common. Chloride, chloride. Anion is common. If you want to find out the moving boundary due to the anion, then you have to keep the cation in common. Here we are going to find out the moving boundary due to the cation. The solution must have different colors. Therefore, to see the boundary, what are the things we have to think? If they have different colors, then we can easily see. Or refractive indices. Then we can use the refractive indexes to see the boundary. Then there should be a method to visualize the boundary is very important in this method. Then now you know, if you want to measure a cation, potassium and cadmium here, then you have to keep the anion in common. If you want to find out the moving boundary due to the anion, then you have to keep the cation in common. The same picture is there. Again, is positive, negative. Then what happens? What we are going to measure? We are going to measure the mobility due to the potassium ions. Then what happens? Potassium ions moves towards the negative direction. If you have a potassium chloride and the cadmium chloride, if the boundary is starting from here, positive ions moves towards the negative terminal. And cadmium also moving. Both are moving, no? Here boundary is moving, potassium and cadmium also moving. Cadmium 2+. Then what happens to chloride? Cl- moves towards here, no? But it is common same rate. And we call the cadmium chloride as following solution. Following means follow. It follows the potassium plus. Then we call it as the following solution. Then cadmium 2 plus is the following solution. It follows the potassium plus and moves towards the negative terminal. Then there should be a following solution. The circuit is switched on for a period of time, delta t. The displacement x of the bound during this time period is measured. In this system, we supply electric field and give for a given time delta t and measure the distance of travel by the boundary from P to Q and get it as x. This is the way how to do that one. Then we'll consider the speed of movement of the boundary. Speed. With the delta t time, it travels x distance. Then v is equal to velocity is due to potassium plus ions is equal to x over delta t. Potassium plus moves x distance within delta t time. The electric field strength E is equal to J over kappa. Then mobility of potassium ion is equal to what? Mobility is equal to drift velocity over E. Then you can write down mobility of ion U is equal to V over E. I am not saying the potassium or negative or positive ion. While you are writing, you have to write down it. Then mobility is equal to V over E due to the potassium, V due to the potassium plus. And V is what we measured X over delta T. And instead of E, you can write down E is equal to J over kappa. Then you will end up with the another equation which is equal to U is equal to X. What is this one? Instead of this J, you can write down what? I over current over area. Then you will end up with U is equal to X A kappa over I delta T. Then X is the distance traveled by the potassium plus ions. And A is the cross-sectional area. I is the current. Kappa is the conductivity and delta T is the time given to move this much of distance. Then you know all the terms here. Experimentally you can measure. Then you can find out the U ionic mobility due to potassium plus. Then I delta T is equal to I delta T, IT is equal to Q. Then you can rewrite the equation as U is equal to XA kappa over Q. Then this is the way how to get this relationship. U is equal to XA kappa over Q.
Madam, should we memorize this one also?
This one is given usually. But you should know what is A, K, kappa and everything. It is enough. If you need to apply this last final examination, we gave this equation, but student don't know what is A and X and then it will be a problem. We are giving this equation, don't worry. But may try to understand and may get an idea, then it is easy to memorize. So substitute anything, whatever you have, if you have E, then you know how to get this relationship or convert it into E likewise. E, and E is equal to J. This equation also given. Is also given. Okay, we are giving that one. Then Then there are some important points. Higher density of the solution. Which chamber you have to keep? You have two chambers, A and B. Then which chamber usually you should keep the higher density solution? High density one?
A1, A chamber.
A chamber. Why? You know all the time, according to the density also, things are coming to the lower one. Then moving boundary will change. Then what happens? Then what happens? Higher density at the lower chamber. Then we remember that one to mix, prevent the mixing of solution. You know, if the density is high, always try to comes to the lower chamber. Therefore, we have, when you are putting the solution, first you have to think what is the high density one and keep it at the lower chamber. Then cation in the following solution should have a small ionic mobility. Why? What is the cation in the following solution here? We are measuring the mobility of potassium plus. Then what is the cation here? Following solution, what is following solution?
Cadmium.
Cadmium 2 plus. Then assume this one moves from here, potassium. If the mobility of cadmium is high, what happens? It can pass this boundary, there can be a overlapping pair. Then sharpness will, what happens to the sharpness? It disappears. There should be a sharp point. Then otherwise you can see this broadening of this one, because if the cadmium has higher mobility, then it can pass the certain distance here as well. And it can overlap with the mobility of the, due to the potassium ions. Therefore, all the time, following solution should have lower mobility than the potassium plus. Okay. Mobility of cadmium plus should be less than the mobility of the potassium plus. Then, shall we discuss it again? Here, what we discussed earlier from up to here is, if we want to measure the mobility due to the potassium plus ions, then we have to find out the any cation. Let's assume X. But we should find out the same what? Anion. All the time anion should be same. Then anion is same and we are going to measure the potassium plus. And always you have to keep the high density one at the lower chamber and low density one at the higher one. According to this one, cadmium has higher density, therefore it is here. And also mobility due to the following solution cation. This is the following solution. Cation should be less than the following solution of the cation what we are measuring. Then what we discuss up to here. Then the setup is correct and you can find out the X distance correctly. And you can apply that equation what we derived earlier to find out the mobility due to potassium ions. This is the way how to do that one. Then go to the activity 3.2, question number 6. First, try to extract what are the given things there. Can anyone read the question? Can anyone read the question? Can anyone read the question? Can you hear me? Can you hear me?
Yes, ma'am.
Can you read the question?
Question number 6, no, ma'am?
Yeah.
Activity 3.2. May I read this?
Yes, you can. Thank you.
Imagine that you are asked to determine the ionic mobility of a cation Az plus in a given aqueous solution of its salt AB. You are provided with the aqueous solution of two other strong electrolytes, Xb2 and Y2b, where X and Y are metals, one of which could be used as the following solution. All the solutions are colorless. However, the refractive indices of the solution of Xb2 and Y2b are very different from that of the solution of AB. It is known that the solution of Xb2 has a higher density than the solution of AB. The density of the solution of Y2b is less than that of the solution of AB. The ionic mobilities satisfy the following conditions. UXN plus is greater than UAX1 and Z plus, and UYM plus is less than UAZ plus. N plus and YM plus are the cation formed in dissociation of Xb2 and Y2b. Given reasons for your choices, describe how you would determine the ionic mobility of Az plus in the given solution of AB using the moving boundary method. Set the apparatus similar to the figure 3.3. clearly indicates the anode, cathode, and the solutions in the two chambers.
Okay, then what we want to measure? We need to measure the mobility due to the A Z plus ions. Then you have to think X or Y contained in cation we can use. Which one you can use? What do you compare for that one? Density or the mobility?
Mobility.
Mobility. Then what is that one? The mobility of A should be greater than the mobility of the cation. Then which is the most suitable one? Look at the given values and say. Mobility of A should be greater than the cation of a given solution. Which one? X or Y containing one. The same anion is there for both. Then it is okay. Same
X.
anion in both. Then mobility
X.
of A should be greater than the mobility of the cation. Which one is the correct one? X containing ion or Y containing?
X contain.
X, Y. Is it correct, others? Here mobility of the X is greater than mobility of the A. When what happens? If you have a boundary like this, and if A is moving, then A can pass the X. Then the boundary will merge. Broad, sharpener decrease. Then which one is the most suitable one?
Y.
Y, ne? Got it? Because
Yeah,
the mobility of the Y is less than the mobility of the A. A is our cation. Then its mobility should be greater than the other cation mobility. Then it is okay. Then we have to think how to fix the apparatus. Then tell me what is coming to the A and what is coming to the B. AB coming to A or B? AB solution coming to A component or B component, A chamber or B chamber?
B.
B. Why? Density
has
of
more
AB is higher than the Y2B. Y2B. Then if we have like this, then ions are moving from where to where? Then you have to think how to set up this one. Then tell me for the B component, and positive or negative? B component, positive or negative?
P is
Following solution, what happens? The following solution follow it. Then following solution coming like this. This is due to the Y cation. Y M plus. No? Then our A is also coming like this. It follows, follow. It is right. Then cation is coming to this direction. Then we have to set the battery negative terminal like this. Then this is our negative terminal and the positive terminal. Depending on the following solution, you have to think where to where it goes, and our cation goes where to where and set up it. Then this is the way how to do it. Got it? Then you should know which ions are moving from where to where. Likewise, you have to think. Then the boundary at the beginning is at the top and it goes towards the from, if it is P, Q, then it goes from P to Q once we supply the electric potential. When it follow, then it is coming behind our solution. Then we will move to the multi-ion solutions. If you have more ions, then the current density is equal to current density due to each and every ion. Summation you have to get. The sigma is the summation notation. Then you have to add the current density due to each and every ion to get the value. JB is equal to VB, CB, ZB, F. We started from here. Then you can see this one and say conductivity of ions depend on the, then you can write down the conductivity is also is equal to the summation of conductivity of each and every ion, and you convert this one to here earlier. Therefore, look at the conductivity equation and you can say it depends on the ionic mobility, molar charge, and the molar concentration and the charge. Therefore, the conductivity depend on the ionic mobility, concentration, and the charge of the ions. And the ionic mobility depends on total electrolyte concentration, what are the ions present in that solution, total concentration of ions, temperature, and the solvent what we use to dissolve our ions or to prepare the solution. Then these things you should know. What are the things likewise? Then the activity 3.3, question number 4 is, you have unnamed sodium chloride and what is the question? Activity 3.3, question number 4.
Can you move on to previous slide?
This one? Is this one?
Yes, ma'am. Thank you.
What is the question related to this activity? 3.3, question number 4.
I read, madam.
Would you please read the question? Activity 3.3, question number 4.
Okay, madam. Imagine that you are given an aqueous solution of NaCl and KNO3. The concentration of NaCl in this solution is known to be 1 mole decimeter minus 3. The concentration of KNO3 is not known. Describe how you would determine an approximate value for the conductivity of KNO3 in this solution using conductometry.
How to find it? What you can do? You have two solutions. Then how to find out the conductivity of solution? If you measure the conductivity, what is given by the machine? Conductivity due to total conductivity due to each and every ion. B. It means conductivity due to sodium plus Cl minus, potassium plus nitrate minus. The concentration of sodium chloride is given, and also we got the relationship earlier. Conductivity is equal to UB, CB, ZB, F. Ionic mobility of the each and every ion, concentration, ZB and the F. Then if you know the ionic mobilities, then you can get the concentration. You can measure the conductivity of the solution, and the concentration you can get for sodium chloride, it is 1 m. For the potassium chloride, we can say if it is unknown, concentration is C. Then for the nitrate and the potassium both, we can get as C. And apply this equation, and you can find out the conductive concentration of the given solution. The concentration dependence of the ionic mobility. Ionic mobility, what happens when increase the concentration? Mobility, moving of ions. What happens when increase the concentration? You have more ions in a non-volume. Then what happens? Its movements. Ionic mobility, what happens when increase the concentration?
Ionic mobility will decrease.
Sorry. Decreasing.
Yes,
Sorry?
ionic mobility will
Yeah,
decrease.
why? You have to think what happens. Then when you consider if you have more ions there in a unit volume, then it is not easy to move the ions. No? Then there are two effects. One is charge asymmetric effect, other one is electrophoretic effect. Then you should know what is this charge asymmetric effect and what is electrophoretic effect. First one is the charge asymmetric effect. Charge asymmetry, with the name you can get an idea. Symmetric of the charge. Okay. When you consider the figure A, this one is given without the electric field. No electric fields, then if you have plus ions, negative ions are around it. And for the negative ions, we can see plus ions. Likewise, we can see if you consider the positive ions, then negative ions are around it due to the attraction between positive and negative. The ions are there. Then once we supply the electric field, this is anode. Anode means positive or negative.
Positive.
Positive.
Here, cathode is negative terminal. Then what happens? This positive ions moves towards the negative direction. And negative ions moves towards the positive direction, and there can be a charge asymmetric here. Then the electric field is positive to, for this one, electric field is here. Then net electric force for the positive ion is given in this blue color. When you consider this ion, plus is here. Once you apply the electric field, it is given here. Then we can see the charge asymmetric effect here. And the net electric charge is given by this arrow. Then when increase the concentration, this ionic atmosphere, what happens? It increase. Then it reduce the mobility of ions. With increase the concentration of the ions, it increase the ionic environment, ionic atmosphere, and it increase the charge asymmetric effect, and it reduce the ionic mobility. And the electrophoretic effect is when you consider a solution, you know viscosity is there. Viscous force opposes in the motion of ion. Always the ion is moving to the opposite direction of the viscosity, what we discussed earlier. And the frictional coefficient F is there, and V is the velocity of ions relative to the solvent. When you consider the solvent, V is the velocity of B relative to the solvent is VB relative, and friction coefficient is given here, F. When you consider an ion is moving to one direction and solvent is moving to the other direction, and we can see the net force here. This is what is happening here. The reduction of the drift velocity due to the viscosity of solvent is called as electrophoretic effect. Due to the solvent, it reduced the drift velocity, and it is called as electrophoretic effect. And also the ionic mobility is introduced for the infinite dilution. Then how to prepare an infinite dilute solution? Infinite dilute means, what does it mean? What can be the concentration of the ions in that solution?
Low.
Low. Infinite means it should goes to zero. Ne? Very low, it means it close to zero. Therefore, we denoted it by UB0 or UB infinite. It goes to zero, that's why we are zero here. Infinite dilution is given by this infinity symbol. Both are correct. The highest ionic mobility, hence the ionic drift velocity of a given ion, is attained when the electrolytic concentration goes to zero. For a given temperature and a given solvent, highest ionic mobility is given for a solution with the zero dilution. When it means we can't go to the zero, and then it comes to the, it is like limits when the concentration goes to 0, the mobility is given is the highest value. Why? If you have low concentration of this electrolyte, what happens? What happens? Which force is minimum? Which forces are minimum? Viscosity is very low. And also, this one is charge asymmetric effect is, especially when you are going to the low concentration, it reduces the charge asymmetric effect. Therefore, it shows the highest mobility. For a given solvent, electrophoretic effect is same. Then the other one is the Gauss's mechanism, jumping mechanism for a solvent. The ionic mobilities of the hydronium and hydroxide ions have unusually high values in aqueous solution. When you measure the conductivity, we can see conductivity of H plus and OH minus is comparatively higher than the other ions present in the medium. It means when you consider the ionic mobilities, the ionic mobility of the hydronium ion H plus or hydroxyl ions have unusual high values in aqueous medium. Why? This is due to the jumping mechanism that operate in addition to the usual motion through the solvent. Normally solvents are moving. Other than that, we can see the jumping mechanism. This water molecule, hydrogen atom can jump to the OH minus and it forms H2O, and again this one can move with the water molecule. Then always there can be a jumping mechanism with the OH minus and the H2O, and similarly H plus ions and the H2O. Both we can see here. This is H plus, no? It is given by H3O plus, no? That is, we call it as hydronium ion. Therefore, this one can go here. Again, jumping mechanism is there. Therefore, these two ions, H3O plus, OH plus, and OH minus shows high values once you use the water as the solvent. Usually we are using the water, then we can see this kind of high values. Then we will see how to determine the ionic mobility experimentally. Once you measure the mobility of the potassium ions with the different concentrations, you can change the concentration of potassium ions, and you can measure the mobility of the potassium ions. You can use that moving boundary method to measure that one, no? You know, you can measure the mobility by using the moving boundary method. Then you can prepare the setup for the moving boundary method, and you can introduce different concentration of potassium ions and measure the mobility. Then when you measure the mobility with the concentration, you can see a graph like this. This kind of graph you can see. If you want to apply, or if you can convert it into a linear graph, it is more effective for finding out the other values for any concentration, the mobility values for any concentration. Then once you convert this graph, mobility of ion is y-axis is same, but we are getting the square root of molar concentration. Square root of molar concentration. Here we measure the concentration U versus C. Mobility versus concentration. Here, mobility, ionic mobility of potassium versus the concentration, square root of the concentration. Then once you plot the graph, you can see this kind of linear relationship. As you know, if you have a linear relationship, we need less number of data points to plot the graph. But if you have a curve shape one, then we have to get more values to plot the graph and to find out the unknown values. But if you can convert it into the linear form, it will be effective. Therefore, we can see this kind of straight line once we plot the graph for a mobility versus the molar square root of the molar concentration. This is the both graph in one, the mobility and the conductivity. When you measure the ionic mobility with the concentration, ionic mobility with the concentration, we can see this dash line. This is for U versus C. But if you have a way to draw a graph for the conductivity kappa versus concentration, it is a linear graph which goes to 0. When we measure the concentration and when we get the different concentrations and measure the conductivity, then we can see this kind of straight graph. Therefore, the dealing with the conductivity is very easy and very effective to find out the unknown concentration of a solution than the mobility. If you measure the mobility, then we have to convert it into the concentration should be converted into the molar concentration to get the linear graph. Likewise, we have to do lot, but here we can get the direct relationship between the conductivity and the ionic concentration. These are the things what you should know under the session 3. Do you have anything to ask? By looking at this one, say, we then increase the concentration, conductivity will increase and ionic mobility decrease. No? Okay. Then session 4. Relative importance of ionic species in building up of conductivity of a solution. Transport number of ionic species in a solution. Transport number. What does it mean? Transport number. It is a number due to the transportation or transport of ions likewise. Then this transport number for a given ion, you can define as IB over A. IB means for a given ion, let's assume transport number of copper 2 plus. It is equal to current created by the copper 2 plus over total current created by the solution copper sulfate, if it is copper sulfate due to the copper sulfate solution. And also you can divide it by cross-section area, then you will end up with the JB over J. It means current density due to this species B over the total current density. Then you know, instead of the current density, we can write down for a given species, it is equal to VB, CB, ZBF. Well, the velocity, concentration, Z and the F. And the current density of the solution is equal to kappa E, ionic strength by conductivity. Then by dividing the VB over E, we can convert this one into the ionic mobility of the solution. Then the transport number is equal to the ionic mobility concentration ZF. And this one is equal to the conductivity due to the conductivity due to the B species, ionic species B. Then transport number is again equal to the conductivity of the ionic species over the conductivity of the solution. Therefore, there are three relationships for the transport number. One is with the current IB over I, other one is current density JB over J, third one is conductivity of the B species over conductivity of the solution.
Madam, are we giving these equations as well?
This one is given usually. And also we are giving this equation. Conductivity is equal to this one. For a species, this one is given. And then by looking this one, you can convert it into this too. Using this one, you can convert this to this one. Therefore, we are not giving all three equations, but the first one is given. And also the relationship between the conductivity and this mobility is given. Even though we are giving all the equations, then it is difficult to find out what is the correct one. What is the necessary one are only given. Then look at carefully and extract whatever you need. For the CAT exams, I am not giving any equation, I think. You need small ones actually. Okay. Then only one cation and one anion solution. If you have only one cation and the one anion, then you can write down the transport number due to the cation is equal to the current density of the cation over current density of cation plus current density of anion. Solution is electrically neutral. You have this equation. This one is equal to this. Therefore, you can write down J is equal to V plus C plus ZF over V plus C plus Z plus F. And by dividing both by both numerator and the denominator by E, and you can convert this into ionic mobility. Then the transport number is again, you can write down it as ionic mobility of the cation over ionic mobility of the cation plus anion. When you work with these kind of equations, I think you will familiar with them. Transport number is equal to I over IB over I. Conductivity, and every time you can see the same relationship all the time. B species here and the total one is below. Here again due to the ionic mobility due to the cation is here. and the ionic mobility due to both are given. It means total mobility. Q. Then this is the summary. Transport number, current density, V and U. Whatever if you have current density, then you can apply this one. Drift velocity, this one. Then mobility, other one, U, containing one. And when you consider these two, this one, transport number due to the cation and the transport number due to the anion, once you add them together, you will end up with 1. It means if you have two ion system and the transport number due to the cation is equal to the 1 minus transport number due to the anion. Transport number due to the cation is equal to the 1 minus transport number due to anion. Once you find out the anion or cation transport number, then you can find out the other ion transport number easily. Activity 4.1, question number 3. Given reasons, state whether the transport number of sodium ions in a given solution of sodium chloride will remain the same, increase or decrease when some KBr is dissolved in it. What happens actually? You have sodium chloride solution and they are asking transport number of sodium plus ions. What happens once you add small amount of KBr? If we consider the ionic mobility, then mobility na sodium plus. For the below part, what happens? Mobility of ions, total ions, what happens? Just think and say whether it's same, increase or decrease.
Increase.
Sorry,
Increase.
why? What happened to the denominator? For this one, what happens? Increase or decrease? Let's assume current. I sodium plus over I total. What happens? This one. For this one, what happens? Total current created by these ions, what happens? Increase or decrease? It increase, then what happens to the total one?
Total decrease.
Decrease. And here it is easy to work with the conductivity other than the current. You know, conductivity, we are talking in a solution, we are dealing with the conductivity. Then the conductivity of sodium ions over conductivity is another equation that we can use to find out the transport number. Assume that the volume of the solution does not change during the dissolution of KBr. Then what happens? The conductivity of the solution increase. Then the addition of KBr only increase the conductivity and decrease the mobility of the sodium ion. then it decrease the, then you have to think how many parameters. Here, conductivity is given for a sodium ions, then you can convert it into the mobility. Because we are transport number, we have to deal with the mobility of the ion. Then what happens to the mobility of ions when we add something? It decreases. If you have more ions, mobility is, it decreases the mobility. Then it decreases the mobility of sodium ions. It increases the conductivity of the solution. Then it decrease the transport number. Then Hittorf method to determine the transport number is the another experiment that we need to discuss today. Okay. This is the setup of the Hittorf method. You have 3 chambers and this is the negative terminal and this is the positive one. We call this one as L compartment and this one as the R compartment, left and right. It denoted by left is L and R is right compartment. Then at the negative terminal, what happens here? What happens to copper? Here, negative terminal, it is our cathode and reduction take place. Therefore, copper 2 plus deposited as copper solid at the L compartment. Then what happens? The conservation of this here. What happens to the conservation of solution here?
Decrease.
Decrease. When you go into the other side, what happens? Anode is positive terminal and you can see the oxidation here. At the R compartment, you can see the dissolution of copper and copper solid convert into the copper 2 plus. Therefore, copper conservation in this solution will increase this compartment. Then we are doing electrolysis here. After the electrolysis, what we are doing here is close the A. There are 2 taps here. We are closing A and B taps first and open the X tap and collect X and open the Y tap and collect this one. It means when we close the A and B, then we can collect left compartment containing volume, middle one and the right one separately. Then we are collecting X and Z separately and measure the volume and concentration of copper ions in each and every compartment. Especially L and the R. Got it? First, we have to measure the volume and the concentration. Then the total charge is equal to what? Q is equal to what?
CV.
Sorry? IT. Q is equal to I. Then within a time we are supply the current for this electrolysis and we can find out the total charge we supply here from the Q. The amount of the copper ions in the L compartment is equal to the amount of the copper ions in the L compartment is equal to what? Delta N is equal to, initially we use concentration of copper solution, same concentration or same solution. We insert the same solution at the beginning. No? Therefore, it is called as initial concentration of copper, Ci. And final concentration of L compartment we measured. By getting the difference and multiply it by the volume of the solution here, we can get the amount of copper ions in the L compartment. Got it? We know the initial one. Now, what is the content we know? Then we can get Cl minus Ci by V. It means we can get the number of copper moles in the left compartment. The amount of copper ions lost during the deposition. Then there is a deposition. Deposition is there. Therefore, we can say the amount of copper ions N during the deposition is equal to Q over 2F. Q over Q known N. Q is equal to what? NF Z. When you consider the copper, N is 2, F is Faraday constant. Sorry, N is what we need to get, sorry. N is number of moles, then Z is 2. Here you know Q is equal to N F Z. We need number of copper deposit. N is equal to Q over ZF. For the copper, it is copper 2 plus, therefore, Z is equal to 2. There the amount of copper deposit, N is equal to Q over 2F. The amount of copper ions move to the L compartment. Then as you know, copper 2 plus deposited as copper. Then it remove the copper 2 plus ions in the L compartment. Therefore, what happens? Copper 2 plus moves towards the negative terminal copper 2 plus. The amount of copper 2 plus ions moved to the L compartment is equal to transport number of copper 2 plus by Q over 2F. Transport number of copper 2 plus by Q over 2F. This is what is happening at the L compartment. Then delta N is equal to delta N, the concentration of copper 2, the number of moles of copper 2 plus ions in the L compartment is equal to copper 2 plus ions moves towards the L compartment minus Q over 2F, what deposited here. Here copper 2 plus comes to this compartment and certain amount deposited here from the solution. Therefore, transport number copper 2 plus Q over 2F minus Q over 2F, which is equal to minus, because you know when you consider the concentration of the solution is L compartment is lower than the initial one. Therefore, delta N is the negative value and it is equal to minus is here, that is the reason, and you can get the Q over NF 2F out and you can write down it as 1 minus TQR. You do not need to convert this into here. Knowing this one is more than enough. It is the conversion. This is the relationship between delta N and the L. Here what they did is we are getting minus and Q over 2F out and convert it into the 1 minus T copper 2 plus. You do not need to go beyond here, but you should know this relationship. Delta N is equal to this one. It means copper deposited is equal to Q over 2F and copper moved is equal to Q over copper 2 plus Q over T transport number of copper 2 plus Q over 2F. These two you should know. What is happening at the L compartment? By getting the difference, you can get the change of copper 2 plus ions in the L compartment. Total charge carried into the L compartment enough tap A. Compartment through tap A is equal to this one. And for the right compartment, you can say similarly, loss of copper at the right compartment, what is happening? Oxidation is there, therefore copper lost due to the dissolution. It is equal to again Q over 2F. We applied Q is equal to NFE. And we can get the amount of the copper or number of moles of copper by dividing Q over F Z. Z is 2. Therefore, Q over 2F is the dissolution amount lost of the copper. And the amount of copper ions moved to the L compartment is equal to this much. As you know that one from R to it moves towards the L copper. Therefore, we can get the delta N is equal to formation of copper 2 plus ions due to the dissolution, which is equal to Q over 2F minus moving of the copper ions towards the L compartment, which is Q transport number of copper 2 plus, so Q over 2F. This is movement because it dissolves and certain amount moves. Therefore, difference between these two can be used to find out the number of moles inside the R compartment, to get the number of moles inside the R compartment. Got it? Then if you know the total charge given Q, what is Q is equal to IT. It means if you know the supply current for a given time period, we can get the Q value and you can find out the Q over 2F. And also it is same for this one because F is the Faraday constant. If you know the Q, then you can easily find out the value for this one. This value we can easily find. Then here we know this value, but transport number we are going to find out. Then if you can measure the delta NR, it means the concentration of copper in the R compartment minus initial concentration, the difference between two by the volume, because the number of moles is equal to concentration of copper ions in the R compartment after R compartment at a given time after the electrolysis by the volume of the R compartment. We measured these two after the electrolysis. Therefore, we can equalize these two. We know these values and this delta N. Then we can find out the transport number due to the copper 2 plus ions. Then how to find out the transport number of the sulfate ions? If you assume that current through the solution is carried only by copper 2 plus and sulfate ions. If you have a copper sulfate solution, we usually dissolve it in water. But water, H plus and the OH minus concentration is very low. Therefore, mainly current is created by copper 2 plus and the sulfate 2 minus. Therefore, which is a good approximation if it is prepared using the conductivity, water and the concentration of copper sulfate is not too low. If you have high concentration of copper sulfate and we prepared it water, then we can say the transport number due to the sulfate ions is equal to 1 minus transport number due to the copper 2 plus ions. Note. What is that note? At the end of the experiment, you take a sample of solution from the middle compartment through the tap Y and determine the concentration of copper sulfate in it to make sure that it is same as that of the original solution. Why? Why? If it is different, you have to repeat the experiment by applying the current for a given small time, for a shorter time period, for a small time. Why? In this method, we remember that at the end of the experiment, what we assume that the copper ions moves to the L compartment is equal to this one. Likewise, we assume then the concentration of the middle compartment should be equal to the initial concentration at the beginning. Then we can assume only the reactions at the L and R compartments. If the initial concentration is not given, what does it mean? You know Q is equal to IT, no? Then we supply the current for a given time period. If the time period is very high, then this affected to the middle compartment. Therefore, what we are doing is we supply the current for a small time period and do the experiment again and see the middle compartment concentration is equal to the initial one. If it is equal to initial one, then we can say only the experiment is correct. Otherwise, we cannot apply those equations to find out the transport number. Therefore, if it is different, you have to repeat the experiment for a short period time and confirm whether it is equal to the initial concentration. Got it? If you use 0.1 m copper sulfate solution at the beginning, after what should be the concentration of copper sulfate at the middle compartment? It should be equal to 0.1. Yeah, that is correct. Should be same.
That means the purpose of that Y compartment is, madam, to check, is it to check the concentration is the same before and after?
Yeah. Because we are getting here two equation. Dissolution is equal to the removing of the copper 2 plus towards the L compartment. Then it should not be at the middle. It should goes to L. Based on that, we can get this relationship. Therefore, all the time middle compartment concentration should be same. Got it? Oh,
Okay.
then we need all the compartment concentrations to do the calculations. Then what is time now? Okay, we have more time. Then we will move to the session 5, molar conductivity of an electrolyte. The molar conductivity. with the definition, molar conductivity, this is, what is this symbol? What is this symbol? What is this symbol? What do you know? What is this symbol? Lambda, no? Then simple lambda and the capital lambda. Then for a solution, molar conductivity is equal to kappa Y over concentration of the solution. These are for the solution. For the ions, what we are dealing with simple letters. Here, capital letters for the solution to introduce the solution, simple letters to introduce the ionic species relevant things. C is the initial concentration, capital C, and the simple C is the actual concentration. If the thing is fully dissociate, C Y is simple C, actual concentration, this is the solution concentration. And if it is fully dissociate, concentration is equal to 0 for the solution. The physical meaning of molar conductivity of an electrolytic. This is a cube with 1 meter distance and with the area of A. The cell of solution with 1 mole of Y. 1 mole of Y is there, distance is 1 meter and area is A. The volume of the cell of the solution that contains 1 mole of Y is equal to, volume is equal to what? 1 over Cy. Is it okay?
Yeah.
Cy is equal to 1 mole cubic meters. Therefore, the volume of the cell of the solution that contains 1 mole is equal to 1 over Y, conservation of Y in cubic meter. Then, for A by 1, what is A by 1? A is cross-section area by 1. It is again equal to volume.
Volume.
It is equal to 1 over Cm. Then A is equal to 1 over Cm. Then earlier we discussed the relationship between conductance and the conductivity. Then conductance is equal to conductivity A over L. Then conductivity is also there. A, instead of A, you can write down C1 over Cy from here. And 1 over L is here. Then for the L, what is the value? Length? It is 1, no? The distance is 1, no? This is 1, no? Therefore, L is equal to 1. Then you have conductivity kappa Y over Cy, which is equal to conductivity of, what is this one? Molar conductivity of the solution. Sorry. I want to go to the previous slide. Here, molar conductivity of the solution is equal to kappa y over Cy. Therefore, here you ended up with this relationship. This one. For 1 meter, molar conductivity is equal to conductance. This G is equal to molar conductivity. If we can prepare a 1m solution and keep it within 1 meter distance. The two plates are 1 meter distance. Then we can say molar conductivity is equal to the conductance of the solution. Molar conductivity of electrolyte in terms of the molar concentration of constituent ions. Similar what we discussed earlier, conductivity of this solution is equal to the each and every species conductivity, summation of the conductivity of each and every species, and the molar conductivity is equal to kappa y over Cy. Then here you can see lambda y molar conductivity of solution is equal to kappa b over Cy. Kappa b over Cy means, what is for this one, what you can write? Cb lambda b. As you know, lambda b is equal to kappa b over Cb.
CB.
Then what happens? Kappa b is here. Instead of kappa b, you can write down lambda b Cb. Then for this one, you can write down Cb lambda b. Okay. Then we will move to the question number 38 and see how to do this one. Then let's assume we have this one. PMPXQ. This is the chemical species formula. And you know that one, if Z plus and Z minus are the charges, and here P is there, P number of M should be there, P by M is Z plus, Q by X is Z minus. You can write down like this. If the concentration of the solution is C, then what is the concentration of M is Z plus? Concentration of M is Z plus, what is the value? It dissociates now. If you have sodium carbonate.
C.
Then it dissociate sodium plus 2 and carbonate. Similarly, if the concentration is C, then sodium plus concentration is 2C and the carbonate concentration is C. Similar to that, if you have C concentration of this solution, M containing PC concentration, because this is the stoichiometric coefficient times C, and the Q times C is the concentration of X in this solution. Then the conductivity of the solution is equal to the conductivity of the molar conductivity of solution is equal to the molar conductivity of solution given by each and every ion. Therefore, we can write down this capital lambda y solution molar conductivity is equal to summation of CB lambda B over C. Cy means the solution concentration. Then CB means the concentration of the each and every species. If you consider the M Z plus, this concentration is equal to PC. Cy is equal to the solution concentration we got here as C. And lambda M is Z plus, molar conductivity of the M species. And the second one is due to the X2 minus, sorry, is XZ minus concentration, XZ minus, then Q times here, Q is the stoichiometry, QC over C lambda XZ minus. Therefore, we can cancel out here C to C, and you will end up with this. You can cancel out C to C and C to C, and you will end up with this relationship. Molar conductivity of the solution is equal to P times molar conductivity of the M species plus Q times molar conductivity of Z species, sorry, X species. Therefore, by looking at this equation, you can write down the molar conductivity of a given solution is equal to stoichiometric times the ions plus stoichiometric times the other ions molar conductivity. Then you should know how to write down the molar conductivity of solution with the molar conductivity of the species. This is for a weak acid like HA, it means like acetic acid. Then you know these are not fully dissociate. If it dissociate fully, then it dissociate to the ions fully. But if it is not dissociate fully, and we assume that at the beginning you have 1, and after the equilibrium we have, if we dissociate alpha amount, we have alpha H plus and the alpha A minus. Then at the equilibrium we have 1 minus alpha HA. Then we can write down the molar conductivity of the solution is equal to concentration of the H plus, here H plus, over C HA, concentration of A minus over this one. And you know that one concentration of the CH plus and the CA minus is equal to alpha times CHA. If we have C concentration, it forms alpha times C concentration at the equilibrium. Therefore, we can write down alpha CHA instead of H plus and alpha CHA instead of the A minus. Then you can cancel out CHA is to CHA here and CHA to here and here. Then you will end up with molar conductivity due to HA is equal to alpha times molar conductivity of H plus and the A minus. We have to add the molar conductivity due to the H plus and the molar conductivity of the A minus. Then the relationship between molar conductivity of electrolyte and the mobilities of constituent ions are given here. For a species, molar conductivity of species B is equal to conductivity of the B over concentration of B. And the conductivity of B is, this equation is given in your exam if you need it, then kappa B is equal to UB, CB, ZBF. Then you can introduce this one to here, and you can cancel out CB and CB, and you will end up with lambda B is equal to UB ZBF. U is the mobility of the ions. Therefore, this is the relationship between the molar conductivity and the mobility of the constituent ions. The relationship between molar conductivity and the mobility of ions is given. Then for the solution, we can introduce it again. For instead of lambda B, we can introduce UB ZBF. As a note, molar conductivity depends on the electrolyte concentration in the solution due to the concentration dependence of the ionic mobility. This molar conductivity depends on the concentration of the solution because this concentration dependence of the ionic mobility. Then the concentration dependence of molar conductivity. Then you have idea the molar conductivity depend on the concentration. And also at the earlier we introduced mobilities for a limiting mobility or for a infinite dilute solutions. Similarly, we are introducing limiting molar conductivities. Limiting molar conductivities. It is independent of the other ions present in the solution. In limiting molar conductivity, even though you have other ions, it not depend on the other ions in the solution. And Corot's law of the independent migration of ions, you can apply at the non-zero concentration. We will introduce the law later. And at non-zero concentrations, molar conductivity of ion depend on the nature and the concentration of other ions present in the solution. For a non-zero concentrations, it means the concentration is not zero. This molar conductivity depend on the nature and the concentration of other ions in the solution due to the charge asymmetric effect and the electrophoretic effect, what we discussed, which affected to the ionic mobility. These two affected to the ionic mobility, and ionic mobility depend on the concentration. Therefore, it depends on the, it affected to the molar conductivity as well. Then this graph shows the variation of the molar conductivity with the concentration of the solution. This is given for the molar conductivity of the solution. For a HCl, you can see this kind of straight line. When increased here, what is given? Square root concentration, square root value of the concentration. With the concentration, it decreases gradually. For KCl, similarly, these two are solution. Once you prepare the solutions with these two ions, they fully dissociate. Therefore, we can see this kind of straight lines. But when you are going to the acetic acid, we can see this kind of curve-shaped line due to the partially dissociation of acetate ions and the H+ ions. A slight decrease in molar conductivity as the concentration is increased. Then when increase the concentration, conductivity decrease. The reduction of ionic mobility brought about by the charge asymmetric and electrophoretic effect. because of the charge asymmetric effect and the electropoietic effect, it reduced the ionic mobility, therefore it reduced the molar conductivity. Then partially dissociate at non-zero concentration. Non-zero concentration, partially dissociate at non-zero concentration, and degree of dissociation decrease as the concentration is increased. Degree of dissociation increased when increase the concentration. The degree of dissociation becomes unity at the infinite dilution. When it goes to the dilution, it means low infinite dilution. What happens? Degree of dissociation become unity. And this is the Onsager limiting law, which is introduced for the limiting solution, the relationship between the limiting solution and the limiting molar conductivity. This is limiting molar conductivity of the solution. This is molar conductivity of the solution. This is the Onsager limiting law, which is given for the relationship between the molar conductivity of solution with the limiting molar conductivity. This limiting law, Onsager limiting law, is applicable only at very low electrolyte concentrations. Typically, it should be less than 0.002. It is applicable for the very low concentrations. Concentration is less than this is not the exact value, just small, it's introduced for the small concentrations less than 0.002 m. And determination of the limiting molar conductivities for a strong electrolyte and a weak electrolyte. There are two types. As I mentioned earlier, strong electrolyte means it fully dissociates. Weak electrolyte means partially dissociate. If it is fully dissociate, this is the limiting law equation, and we can use this equation and convert it into the y is equal to mx plus c to find out the limiting molar conductivity of the solution. Limiting molar conductivity. Therefore, it is a graphical method, and you have to plot the graph. This is the y-axis, molar conductivity of the solution, and square root of the concentration of the solution, and you will end up with y is equal to mx plus c equation. Then the intercept c is equal to the limiting molar conductivity of the solution. Then graphically, you can find out the limiting molar conductivity by using this relationship. Here, this is the Onsager equation, lambda y, it is given here, and this is the value, and slope is given, it is a minus value. Therefore, you can see this kind of relationship. If it is minus, then we will end up with minus mx plus c. Then usually we are giving this one for a positive sign, but if the graph is like this, it means the intercept is always the limiting molar conductivity of the solution. We are not worrying about it is positive graph or a negative graph. Usually we are plotting the graph and see the slope and find out the limiting molar conductivity from the intercept. For a weak electrolyte, we are not using a straight line type graph. It means we are not plot a graph. Use an indirect method. For an example, if you want to find out the limiting molar conductivity of the HAC, acetic acid. Then what we are doing here is we are making this solution by using sodium acetate. It is fully dissociate and HCl also fully dissociate. To remove that one, we are getting the acetate from sodium acetate. H from the HCl solution. To remove the sodium and chlorine, we are getting sodium chloride. Then what we can do is the limiting molar conductivity sodium acetate is equal to limiting molar conductivity of sodium ions plus limiting molar conductivity of acetate ions. HCl again, we can add the H plus limiting molar conductivity and the chloride minus limiting molar conductivity. Then sodium chloride similarly you can get. To find out the limiting molar conductivity due to the acetic acid, what you have to do? We need only acetic acid. Then what we have to do? We can use these strong electrolyte solutions to find out the limiting molar conductivity due to the HAC, which is equal to the limiting molar conductivity. We are H getting from the HCl, therefore limiting molar conductivity due to the HCl plus HAC. Acetate ion is getting from the sodium acetate. Then we are getting sodium acetate limiting conductivity minus chloride and sodium is in excess. Therefore, we have to reduce the limiting molar conductivity due to the sodium chloride. It is given in here as an equation to get the limiting molar conductivity only due to the acetic acid. This is the way how to do the calculation, and it is an indirect method. Then you should know how to do this equation and how to find out the limiting molar conductivity of the acetic acid solution. If the acetic acid solution is given, then you should know it is equal to the limiting molar conductivity of acetate ions and the sodium ions separately. These are the things I hope to discuss today. And you have another day school on 1st of October. Then I hope to get 1 hour on that day to complete the last session and discuss
Yes,
some
ma'am.
questions. Thank you.
Thank you. Madam,
Yeah.
Madam, can you